All right, Chemistry 3112. This is our last lab lecture of the year. And the last assignment that you'll have to do is this combined spectroscopy worksheet. And it's going to be due for everybody on November 30th. So it is due on November 30th. That is the Monday after the Thanksgiving break. And let's just take a quick look at this spectroscopy worksheet. The instructions are here. It asks you to provide molecular formulas, or sorry, if you're provided a molecular formula, calculate the unsaturation number. That's the hydrogen deficiency index for problems that the molecular formula is not provided. You're going to have to provide that. And of course, then you would still provide the HDI. For IR, you're going to want to annotate the major peaks. So if there's, for example, a carbonyl stretch or a carbon-oxygen stretch or a oxygen-hydrogen stretch from a carboxylic acid, whatever, you want to indicate that. You're going to annotate the mass spectra. And so the way you would do that is you want to make sure that you apply the nitrogen rule. So, and you want to identify if there's any halogens. So you want to identify if there's any bromine or chlorine present in the molecule. And then you don't have to annotate everything, but you're going to use it, the mass spectrum, to help you determine the structure of the compound. For the NMR, you're going to draw individual structures for each spectrum. So if there's a carbon and a proton, you're going to draw it twice and you annotate each. Remember that you label the signals in the spectrum starting at the far right, A, B, C, D, so on and so forth. And then you put the appropriate letter next to the appropriate carbon or hydrogen in the molecule. And then for full credit on NMR, be sure to be very clear on the annotation and very clear on the placement of those letters. Well, let's take a look at the kind of problems that I asked. Here's the first one. You can see that you're given a beautiful molecular formula. It asks you to calculate the U, or the HDI. Remember that U is the same thing as the hydrogen deficiency index. So you just use the equation. Then you see you have a big absorbance here, and so you're going to report what that absorbance is. And if there's any others, of course, you're going to report those as well. I give you a proton and a carbon, and of course, you want to write the structure here, and you're also going to write the structure here, and then you would identify all of the protons and the carbons in those spectra. The next one is in the same vein. I give you an IR, a proton, and a carbon spectrum. The third one is similar. I'll give you an IR, a proton, and a carbon spectrum. I've also labeled all the peaks with letters to make things easy for you. And then the next question says, determine the structure of the molecule from just a proton NMR, annotate the spectrum. And so here I've given you a formula. I ask you to calculate the HDI, and you're going to come up with a structure from that. The next one is in the same vein. I just give you an NMR, nothing more than that. You're going to put the structure. You're going to annotate it correctly using the letters. The next one's the same thing, just NMR. Number 7 is just NMR. When it says SEPT here, that means it's a septet, okay? So this would be a singlet, this would be a doublet, so SEPT, that stands for a septet. Next one, another NMR problem. Number 9 is an IR. An IR and a mass spec, and it gives you a little bit of a clue about the proton NMR. So just using this information here, the IR and the mass spec, you should be able to determine the structure of the product, or the compound, sorry. Next one, I also give you an IR, I give you a little clue about the carbon, and I give you a mass spec, and with that, you should be able to determine the structure. And the very last question, question 11, asks you to assign stereochemical configuration, R or S, to each of the following molecules. So we have 4 times 4. So we have a total of 16, and you want to assign a stereochemical configuration to all of those. And that's the entire assignment right there. So again, if we go back to the first slide, this assignment will be due on November 30th for everyone. And again, that's the first day after we come back from Thanksgiving. Remember that you have to submit this as a PDF on our class's Canvas page. Also, I've been looking at some of the students' PDF submissions. Not only should you take a picture of it and convert it into a PDF, but you should also change it to black and white. I noticed that some people just basically took a picture of it and uploaded that, okay? You want to convert it to black and white. It's much easier for the grader to look at the contrast and to grade it when it's in black and white. Okay, well, let's take a look at some practice problems. And we're going to look at spectroscopy practice problems today. And these are practice problems from the ACS study guide. And so I was hoping that these would kind of get the ball rolling if you haven't thought about spectroscopy in a few weeks. And so we're going to start with question number 1, which asks us which ketone will show a carbonyl absorption at the lowest frequency in reciprocal centimeters in the infrared spectrum. I'm going to give you a second to look at that and see if you can come up with an answer. And once you've done that, we'll take a look. Also, if anybody wants to propose an answer, please feel free to type it into the chat. Does anybody have an answer for this one? I have 4 ketones, and it's asked me which one of these will show a carbonyl absorption at the lowest frequency in the infrared. Well, you might remember that a ketone, carbonyl, yes, there we go. Okay, so a carbonyl of a ketone will have an absorption somewhere around 1715 reciprocal centimeters. But remember that wave number is equal to 1 over 2 pi times the speed of light multiplied by the force constant over the reduced mass to the power of a half. The force constant, this is the same thing as the bond strength. And since B has a resonance structure that we could draw like this, I'm not going to draw it out, but since it has a resonance structure, this carbonyl, this carbon-oxygen double bond is weaker than all of the others because of resonance. So because of resonance, it is weaker. And since the force constant is in the numerator, that's going to give me a lower wave number. And so the answer is B. Question number 2, we have an infrared spectrum, and it asks us which compound is consistent with this infrared spectrum. I'll give you a quick second to take a look at it. There's one of them that I think is abundantly clear here. Yeah, my students are all saying C. Why did they all know it's C? Well, you can see we have a broad stretch here. This is the oxygen-hydrogen stretching from an alcohol. So this is alcohol OH stretch, which falls in the range of 3600 to around 3200. So we'll put here 3600 to 3200. So we have that broad stretching. And the reason we have broad stretching when we have an alcohol is because of hydrogen bonding, which stretches that bond and weakens it. And so the only compound in here that has a hydroxyl in it is C. Here we have an ester, aldehyde, and a ketone, but C is the only one that is an alcohol. And so the correct answer is C. Number 3, this one's made a little bit simpler because I crossed out a couple of the answers. Anyhow, there's less scribbling as we move forward here. But question number 3 says, which is the most reasonable structure for the compound with this infrared spectrum? I'll give you a second to look at it. All right, we get some different answers here. Well, the first thing I notice about this is the biggest stretch in the entire spectrum is right here. Okay, so if this is 1,000 and this is 1,100, this is around 1,250, something like that. When we have an ester, the carbon-oxygen stretch of an ester, so we'll put ester, carbon-oxygen stretch. Okay, it falls in the range of 1,300 to 1,000 reciprocal centimeters. And you can see that this is right kind of in between 1,200 and 1,300, so maybe around 1,250. Also, an ester has a carbonyl, and that carbonyl, this is the C double bond O stretch of an ester, is around 1735. And so there's our carbonyl stretching. Well, it's not going to be the second compound because that's an alcohol, and it's not going to be the third compound because that's an aldehyde. Oh, sorry, that's a ketone. Also, number 4 is an aldehyde. Another problem, the reason why it can't be D is because we don't see aldehydic CH stretching. Remember that aldehydic CH stretching comes out at around 2850 and 2750 reciprocal centimeters, and we don't see that at all. This stretching that you see here is just plain old sp3 carbon-hydrogen stretching. What else do you see in the spectrum? Well, I notice that there's one other signal of importance in here, and that's this stretch right here for the alkyne. Alkyne stretching, carbon-carbon triple bond stretching, is in the neighborhood of 21 to 22, or sorry, 2150 to 2100. And it's kind of hard to see here, but we have 2100. This is around 22 here, so it's in that neighborhood. And of course, it's going to be a little bit more deshielded because it's next to a carbonyl, so it's going to be a little bit higher than that 2150. So we'll label this as our carbon-carbon triple bond stretching. And so that means that the answer is going to be A. Great. Let's try number 4. I'll give you 10 seconds to solve number 4 very quickly. All right, somebody put in an answer immediately. I'll give you a few more seconds to think about it. Yeah, perfect. You got Sean and Andrew who've chimed in, Kyer, and all of them are correct, right? What did they say? They said, well, look at this. I have this really broad signal right here. That's oxygen-hydrogen stretching. So we'll say this is an OH stretch, but this is from a carboxylic acid. So this is the OH stretch of a carboxylic acid. So we'll put carboxylic acid OH stretch, right? Because that's very broad because of the pronounced hydrogen bonding. It's usually in the range of 3,300 to around 2,400, a very, very broad range. Okay, what else do we see? We have a nice big signal here. This is a carbonyl, right? Carbonyl stretching, to me, it looks like it's a little bit less than 1,700. We'll put that that's around 1,700 maybe, but that is the carbonyl stretching from the carboxyl group. So we'll put carbonyl stretch from carboxylic acid. Okay. Well, if we look at A, we have an ester, so it can't be A. If we look at D, we have an aldehyde, so it can't be, sorry, C, is we have an aldehyde, and if we look at D, we have a ketone. The only one that has a carboxyl is B. Since we have a carboxylic acid, the answer has to be B. Question number 5. This is a good one. I think this is a really good question. Very well done. Which structure is most consistent with this infrared spectrum? I'll give you a second to take a look at it. Okay, I see we have a few answers. Let's see what we have in here. The first thing I notice is that above 3000, we have a pretty pronounced signal here, and there's two peaks in this signal. Okay, when I have two peaks that are in this 32 to 3500 range, this is a primary amine. Primary amine. Okay, another way to write that would be just to say RNH2. Right? Why do we see two signals? Because we have symmetrical stretching and asymmetrical stretching. That's why we get two peaks with a primary amine. Well, that's going to remove this one. All the rest have primary amines in them. Now, I see some other really big signals in here. That would be these two here. There's one around a little bit above 1600, maybe one around 1475. Okay? Remember that when we see aromatic stretching, it's usually 2 to 3 signals in this range, around 1600 to 1450, and give or take a little bit. And so this is carbon, we'll put here that it's aromatic, carbon double bond, carbon stretching, okay? We want to let the reader know that it's aromatic. Now, I know that something students love to look for are overtones, right? You can see overtones in the spectrum on the next problem, or it's question 7. Even though we don't really see pronounced overtones here, you don't have to have overtones in order for it to be an aromatic compound. So that's going to eliminate A, because A is not aromatic. Well, then our choice is either going to be B, which is aniline, or D, which is paramethyl-aniline. Could anybody figure out if it's going to be B or D? Well, which one do you think it might be? I'll give you a clue. The answer is right here, okay? In this big group of absorbances just below 3000. This is sp3 hybridized carbon-hydrogen stretching. Okay? Aniline has no sp3 carbon-hydrogen bonds, whereas paramethyl-aniline does have sp3 hybridized carbon stretching. And so the correct answer is D. Give me a thumbs up if that makes some sense now that you see. You're like, seems reasonable now. You can see some aromatic stretching here. It's not very pronounced, Andrew, but where's my blue pen? If this is 3000 here, you can see that there's something here, okay? Again, it might be buried, but it still is the best answer. It's the only one that meets all the criteria. For sure, it's aromatic. For sure, it's a primary amine. And the only way it could have the sp3 hybridized stretching is in order for it to have an sp3 hybridized carbon atom in there. Number 6. More IR. Which compound corresponds to this IR spectrum? I'll give you a second to take a look at it. Does anybody have an idea about this one? Somebody says D. Somebody else says C. Well, there's a couple signals that I notice here. Okay, I got a bunch of different answers. What if I circled this signal here, which is quite pronounced this time, and this signal here? The signal in blue is around 3100. This is a result of sp2 hybridized carbon-hydrogen stretching. The signal here, which is around maybe 1640 or something like that, it's around 1640 reciprocal centimeters. This is going to come from a double bond between two carbons. So this is carbon double bond stretching. It's not aromatic because I don't see a cluster of peaks around here. Also, there's no aromatic compounds in there. Another thing, I noticed that somebody said D, but there's no carbonyl stretch in here. Right? If we were going to have a ketone or an ester, we'd have to have a carbonyl stretch greater than 1700. And we don't have that. So it's definitely not an ester, and it's definitely not going to be a ketone. Another thing is, if I was to have sp hybridized carbon-hydrogen stretching, that shows up around 3300 reciprocal centimeters, right? Which would be closer to around here. And I don't see that at all. And so this compound must be an alkene. And the only one that fits the bill is A, the alkene. Let's try number 7. Which compound would produce this IR spectrum? I'll give you a few seconds to look at it. Good. Thanks, Andrew. There's one thing in here that's a dead giveaway, right? One thing I always look for. And this is these two signals right here. These are a result of aldehydic, what's called aldehydic CH stretching, which occurs at around 2850 and 2750 reciprocal centimeters. So this compound must be an aldehyde. Not only that, but we see the aromatic carbon-carbon stretching, which is probably all of these signals right here. This would be aromatic carbon-carbon stretching. We also see overtones, which lie between 1667 and 2000 reciprocal centimeters. And again, Andrew, you can't really see the sp2 hybridized carbon-hydrogen stretching for the aromatic, or we don't see anything really super pronounced there, but it could be buried, right around here somewhere. There we go. The only possible answer is A. The dead giveaway here would be the aldehydic stretching here. You'd have to know that. Question number 8. Now we're getting over to NMR. It says, which is the correct order from lowest to highest field for the chemical shifts of the numbered sets of protons in the proton NMR spectrum? Well, remember that when we look at this NMR spectrum going from 12 to 0 ppm, that this region on the far left is called downfield or low field. Okay, and then here this is upfield or high field. So if we're going from lowest to highest, which one of these is going to be deshielded the most? Well, the protons that are sandwiched in between an oxygen and a bromine are going to be the most deshielded. They're going to be at lowest field. This is the only possible answer, because if those protons are going to be the lowest, the ones that are next to the oxygen only are going to be second, And then the ones that aren't next to a heteroatom are going to be third. Let's try question number 9. Question number 9 asks us, which of these compounds will show two triplets among other signals in the proton NMR spectrum? We have these three compounds right here. I'm going to go ahead and draw the bond line structures of all of those compounds. So the first compound is this. Okay, and we're looking for compounds that have at least two triplets. Okay, remember the question asks, which of these compounds will show two triplets among other signals in their NMR spectra? So we're looking for two triplets. Okay, I'm going to give you a second to examine these compounds and see if you can figure out which ones have two triplets. Or maybe there's just one. Okay, let's examine these compounds. If I look at the first compound, I see that these two protons here, which are equivalent, are both coupled next to two protons. And so I would get a triplet from these two protons. If I look at this proton over here, it's also coupled next to these two protons, and so it would also give me a triplet. Whereas these two protons here are coupled next to this proton and these two protons, which are not equivalent, and so that would not give me a triplet. It would actually give me a doublet of triplet or a triplet of doublets. And so this compound would give us two triplets. We can cross D off of the list. If we look at the second one, if we examine these two protons, they are coupled next to the two protons in the center, so we'd get a triplet. These two protons would also give us a triplet, but it would be the exact same triplet, wouldn't it? Because there's a plane of symmetry down the molecule. And then finally, the two protons in the middle are coupled next to four protons, so that are all equivalent, so we would end up with some kind of quintet. So this is not one of the answers. So we can cross A off. Well, now we just need to look at the last one. If you look at this proton, it's coupled next to the two protons in the middle, N+1 rule, this will give me a triplet. If I look at this proton here, this will also give me a triplet because it's coupled next to these two protons, but there's also a plane of symmetry down this molecule. So it will give me a triplet, but it's the same triplet that was over here. Then, if I examine these two protons here, they're coupled next to 1, 2 protons that are identical. So, based on the N+1 rule, this one will also give me a triplet. And therefore, the answers are, this one will give me 2 unique triplets, and the first one will give me 2 unique triplets. So the answer is C. Okay. Question 10, it's hard for me to squeeze the entire thing on the screen. I'll just maybe help you out with this one. The answer isn't D. So if the answer isn't D, let's make it simple. It's got to be either A, B, or C. Which one of these proton NMR spectra is consistent with that of ethyl methyl sulfide? Well, if we examine ethyl methyl sulfide, you can see that these protons here, these three protons, are all equivalent because they're on a methyl, and they're not split by any protons. So I'm going to have a singlet that integrates for 3 protons. Here I have a singlet that integrates for 3 protons. Here I have a singlet, and here I have a singlet. They all integrate for 3 protons, and they all have the same chemical shift. That doesn't get us any further ahead, does it? Next, I have a methylene. These 2 protons are coupled next to 3 protons, so this should be a quartet that integrates for 2 protons. In A, I don't have any quartet that integrates for 2 protons. I have a quartet here, but it integrates for 3 protons. And so I can cross A off the list. But if I look at B and C, I have a quartet that integrates for 4 protons here. Or sorry, I have a quartet that integrates for 2 protons here. And here I have two protons integrating or giving me a triplet. So the answer has to be B. And then if I look at these 3 protons here, they're split by the 2 methylene protons, and so I would have a triplet that integrates for 3 protons, which matches this as well. And so my final answer is B. You can also see that the de-shielding lines up, right? The quartet that is the result of the 2 protons is the most de-shielded, and the least de-shielded is the triplet because it's the furthest away from the sulfur. All right, question 11. How many signals would be observed in the proton decoupled carbon-13 NMR? So proton decoupled just means our standard proton NMR. I'm going to write out the bond line structure. Maybe that'll help somebody. Okay, I'll give you a second to think about how many different carbon-13 signals would you get from this molecule. So I'm looking for the total number of distinct carbons in this molecule. All right, well, let's examine it. If you think about this tert-butyl group here, there's free rotation around this bond. And so that means that all 3 of these carbons, all 3 of these methyl groups will be equivalent. That will give you 1 signal. Okay, those 3 methyls are all equivalent. What about this quaternary carbon here? It's unique. There's no other quaternary carbon like it in the molecule. The same thing applies to this quaternary carbon here. There's no other carbon like it in the molecule. This is the only CH2 in the molecule here. Then we have a methyl group all by itself. And we also have this methylene all by itself. This gives us a total of 1, 2, 3, 4, 5, and 6 signals. And so that's our final answer. 6 signals for this compound. Question 12. Which structure is consistent with the proton NMR spectrum? I'll give you a second to look at it. All right, I got a few different answers here. A couple of things. First thing is when I have a signal that's at 10 parts per million, this comes from an aldehyde. Right? A carboxylic acid hydrogen, that's around 12, but an aldehyde comes around 10 parts per million. This doublet of doublets that's shown here, these are aromatic. They fall in the aromatic region, but not only that, it means that the ring is para-substituted. When you have a doublet of doublets tilting in towards each other like that, that's para-substitution. So that means that our ring has to look like this, and it's going to have a substituent on each side like that. And the substituents will be different. Then down here, you can see I have a quartet and a triplet. This is usually coming from an ethyl group. Well, the only one that meets all these criteria is C. I saw that somebody put A, which is a good guess because we have an aldehyde, we have an aromatic ring, and we have an ethyl group. The problem is that it's not para-substituted. Whereas this aromatic ring is para-substituted. All right, let's give number 13 a try. Which structure is consistent with this proton NMR spectrum? You can see I have a doublet that integrates for 6 protons. Then I have a multiplet that looks like 1, 2, 3, 4, 5, 6, 7 peaks. That integrates for 1 proton. I have a doublet that integrates for 2 protons, and then I have a singlet that integrates for 1 proton. Let's look at the possible answers because the answer is there. You can see that all of these are alcohols. So that means that this 1 hydrogen around 4 parts per million, this comes from the alcohol. Because alcohol hydrogens lie in the range of around 2 to 5 parts per million. The answer can't be A. Could anybody tell me why it can't be A? Exactly. Andrew says there's no singlet integrating for 9, right? There's no T-butyl in the NMR spectrum. B doesn't work either. The reason why is because if we write the multiplicity above each group of hydrogens, here we'd have a triplet, here we'd have some kind of sextet, here we'd have some kind of quintet, and here we'd have some kind of triplet. We definitely don't have 2 triplets in there, so that one doesn't look reasonable either. If we go down to D, this group of protons here is coupled next to 2 protons. That would give me a triplet. This group of protons here is coupled next to 1 proton. That would give me a doublet. I have my singlet from my alcohol. This proton here is coupled next to 5 protons, and so that would give me a sextet. And this guy here is coupled next to 4 protons, and so that would give me a quintet. Still doesn't match our spectrum. But if we look at C, we have the singlet. We have these 2 methyl groups, which are equivalent. They're both coupled next to 1 proton. This is the only thing out of any of these structures that would give me a doublet that integrates for 6 protons. I have my CH2, which is coupled next to 1 proton. That's going to give me a doublet. And then I have this guy here, which is coupled next to a lot of protons. It's actually coupled next to a total of 8 protons. We generally don't see splitting past 7 peaks. And so this would be responsible for this multiplet here. And so the most reasonable answer is C, which if we draw the bond line structure, this compound, just 2-methyl 2-propanol. Okay, number 14. Which structure is consistent with this proton NMR spectrum? Just 3 signals. I'll give you a second to think about it. If you think you have an answer, feel free to type it into the chat. The first thing I noticed about this spectrum is that we only have 3 signals, and all are singlets. No multiplicity in here whatsoever. I have a peak above 7, and so this signal must come from aromatic protons. Okay. Then I have a signal at around 5 parts per million and another one around 2 parts per million. Are there any of these possible answers that are impossible that you notice right away? Of course, 3 of them are impossible, but is there anything that kind of you just look at it very quickly and say, nope, impossible. Cannot be those. Exactly. Thanks, Andrew. Great answer. So Andrew answered very quickly, B and C. It cannot be B and C because there's 2 ethyl groups, right? 1 in each one. Remember in an ethyl group that the methyl is going to integrate for 3 protons, but it's going to give us a triplet. And the methylene is going to integrate for 2 protons, but it's going to give us a quartet. And since we have no triplet or quartet, it can't be B and it can't be C. Another thing that I noticed right away that kind of gives me pause that it can't be D is that D is para-substituted. Okay, when we have para-substitution on a ring, in the aromatic region, around 7 parts per million, we're going to see a doublet of doublets that are going to lean in towards each other like that. Okay, and since we don't see that doublet of doublets around 7 parts per million, that tells us that it's not para-substituted. Before we just go ahead and say the answer is A, I want to show you one more thing. You might remember a table that we looked at way back in chapter 15 in Organic Chemistry 1 that was found in Klein, where he had some quick rules for calculating or estimating chemical shifts for protons based off of functional groups. You might remember that the baseline for the protons in a methyl group was 0.9 parts per million, but when they're next to a carbonyl, we add 1 part per million. So we would get around 1.9 parts per million for these protons. So if I was to call these A, these would be the A protons here. If I look at this methylene, the baseline for a methylene was 1.2, but when it's next to the oxygen of an ester, we add 3. That would give us 4.2 parts per million. Now you might be saying, well, come on, this is higher than 4.2 parts per million. But it's also attached to an aromatic ring, which is going to pull electron density away from it and de-shield those protons even more. And so the chemical shift should actually be greater than or equal to 4.2. And so that seems reasonable. All the other protons are found in this singlet right here. There's no distinguishing them in this spectrum. Let's try number 15. It says the chemical shifts in the carbon-13 NMR spectrum for this compound are 15.8, 40.1, 51.8, and 170.2 parts per million. Which is the correct set of chemical shifts for the carbon atoms? This is called a carbamate. It's a functional group we haven't looked at in our class, or if we did, I don't remember. Anyhow, if I number these carbons 1, 2, 3, and 4, obviously the carbonyl is going to have the highest chemical shift. It's going to be the most deshielded. It's going to be around 170.2. And so that means the answer is either C or D. Another one that I think is probably a no-brainer is the fourth carbon, because it's not next to any deshielding atoms. Carbons 1 and 3, those are both next to oxygen or nitrogen, which are deshielding. Whereas this carbon is in the beta position with respect to the nitrogen, so it's not going to feel much of an electron withdrawing effect. And so it should be the least deshielded of all the carbons in the molecule. So it should have a chemical shift of around 15.8. That would mean the answer would be D. It's the only possibility that lines up with our two assessments. Let's take a look at carbons number 1 and number 3 to see if they make sense. Well, you see that their chemical shifts aren't that far apart, 51.8 and 40.1, but carbon number 1 is attached to an oxygen. Oxygen is more electronegative than nitrogen. Therefore, it's more electron withdrawing. Therefore, it's going to deshield that carbon even more. And so D starts to make even more sense. Question 16 is something I want to address with you guys. This is something you see in the ACS study guide. It didn't come up in, or it doesn't come up in Klein's textbook. Is which structure is most consistent with the carbon-13 NMR spectrum? You notice that you see the letters Q, T, and D above these singlets. When you see a Q, it's kind of like a version of the N+1 rule. It means that that would give you a quartet. Now they've resolved this peak so that it just gives you a singlet. But what the Q means is that that carbon is attached to 3 hydrogens. So when you see Q, it means you've got a methyl. When you see T, it's attached next to 2 protons, so that's a methylene. If you see D, that means you've got a methyne. And if you see singlet or S, that means you've got a quaternary carbon. Well, based off of that information, in this spectrum, we have 2 methyl groups. We have a methylene, and we also have a methyne, which is the most deshielded. If I look at this methyne, it's got a chemical shift of around 70 parts per million. If you look at the typical values of carbon-13 chemical shifts, when something falls in the neighborhood of 50 to 100, that means that this methyne is going to be attached to some kind of heteroatom or be in a triple bond. Now, all of these answers have heteroatoms. But here in this molecule, I have 2 carbons that are both bound to oxygen. And so I would have 2 signals in the range of 50 to 100. In the next compound, I have a carbonyl. that's going to fall in the range of 50 to 100, but it has no proton attached to it. So it can't be this compound either. So that eliminates A and it eliminates B. Same thing applies to C. We have a carbon that would fall in the range of 50 to 100, and we have another carbon that might fall, somewhere in that range, or maybe close to it, because this carbon is attached to a nitrogen. But again, neither of them are a methine. If I look at this one here, though, here I have a methine that's attached to an oxygen. This is going to fall in the range of 50 to 100 parts per million. I have two methyls that are going to be the least deshielded, and then I have a methylene, which is going to be the most deshielded after the methine. And so the correct answer would be D. This is a good one because it's a combined spectroscopy problem, much like many of the problems that you'll see in the dry lab. Which structure is in agreement with these proton NMR and carbon-13 NMR spectra? Remember, when you see the Q, that means we have a CH3. When you see a T, that means it's a CH2. We have another CH3, another CH2, and then we have a singlet up here. So that means that this is a carbon that has no hydrogens attached. Well, if we look at the possibilities, you can see that we have two methyls, two methylenes, and a carbon with no hydrogens attached in A. Two methyls, two methylenes, and a carbon with no hydrogens in B. Same thing in C. In D, we have 1, 2, 3 methyls, 2 methylenes, and a carbon with no hydrogens attached. Can't be D. We don't have enough methylene or methyls. Another problem with D is that when we have a signal that's above 200, that's going to come from a carbonyl, isn't it? So that means we must have a carbonyl. Since there's no carbonyl here, that's a better reason to say that it's not D, as a matter of fact. Because after I was thinking about it, I kind of misspoke here, right? Because these two methyl groups here are going to be chemically equivalent. So that means we'd have 1, 2 signals for methyls, and then 1, 2 for methylenes. But since it's a hydroxyl, and this can't be a hydroxyl, this carbon right here, so therefore that's why it's not D. Okay, that's a better rationale. So then it becomes a battle between A, B, and C. We have two esters and a ketone. Well, I think in order for us to solve this problem effectively, we're going to have to look at the proton NMR. Well, does anybody else have anything to say about the carbon before we move on? Notice I put 2 marks in green here. Is there anything that anybody notices? What I notice is that in A, I have a carbon-oxygen single bond, and in C, I have a carbon-oxygen single bond. Those would have to fall in this range, and I don't have that. Whereas in B, everything meets the criteria for the carbon-13 spectrum. Now let's check the proton spectrum. If I look at this methyl group here, remember the baseline for a methyl is 0.9 and it's next to a carbonyl. That's going to give me 1.9 parts per million, roughly. Here I have a signal that's just above 2. So that means that these protons would be my C protons. If I look at the other methyl group, this methyl group right here, it's going to be not effectively deshielded at all because it's so far away from the carbonyl. And so this is going to be my A triplet that integrates for 3 protons. Then between D and B, well, I think it's pretty easy to see that B is going to be these protons here because it's coupled to a total of 5, which would give you a sextet. And then D, these 2 protons are coupled next to 2 protons, which would give you a triplet. You can still do the math. The baseline for a methylene is 1.2, and it's coupled, or sorry, it's next to a carbonyl. That's going to give me 2.3 parts per million. And you can see it's in that neighborhood. All right, let's try another one. Number 18. I'm going to give you some time to take a look at this one yourselves, instead of just watching me solve the problems. Here we have a methyl, methylene, methine, methine, carbon with no hydrogens, another carbon with no hydrogens, and here we have methine. Take a second and see if you can figure this one out. Does anybody have an idea about this one? Number 18. Okay, somebody says D. Well, let's take a look at it. First thing I noticed is that all the answers, they're all para-substituted, aren't they? Every last one of them is para-substituted. If I look in the aromatic region, which is between 100 and 150, so that's around this area right here, I have 2 CHs and 2 carbons. That's consistent with a para, and you might be thinking, well, if I have a para substitution, shouldn't I have 1, 2, 3, 4 CHs instead of 2? Well, notice that the relative height of these is about twice of that of any other peak. And you're like, well, it's not twice this and it's not twice that. No, I know. But when they're a lot taller like that, that means that it's probably 2 of them. Okay? So that takes care of these 2 and these 2. Now, I could have done that on any one of these structures because they're all para-substituted. I just chose to do it on the first one. Doesn't mean the answer is A. In fact, it's not A. All right, but now we've taken care of all of the carbons that result in the para-substitution. Okay, so that means we're going to have, besides the para-substituted ring, we're going to have a CH2, a CH3, and a CH. Well, right away, I see that it can't be A because I have 2 CH2s. I only have 1 CH2 in my carbon 13, so it can't be A. If I look at B, it's para-substituted. I have a CH3 and I have a CH2. That looks good. But I don't have a carbon with a hydrogen attached to it, another one. And so the answer can't be B. If I go to the next one, C, hey, this one looks like it meets all the criteria, doesn't it? It's got a CH3, CH2, a CH. What's the problem? The problem is this, is that my CH3 is attached to an oxygen. It should be much more deshielded. When we have a carbon that's bound to an oxygen, that should come in the range of 50 to 100. That would put this in here somewhere. So that can't be the correct answer. If I look at D, and I think that Sean may have suggested D, look, I've got my CH. It's going to be highly deshielded. It's attached to a carbonyl. I've got a CH2 and a CH3, but I've got two of them. But that makes sense. Why does that make sense? Because their relative heights are tall, like these signals here that come from the para-substituted aromatic ring. So now it's starting to make more and more sense. So now I've got my CH2s, my CH3s, my para-substitution, and my CH. My CH2s are not attached to an oxygen, but they are relatively deshielded because they're next to a nitrogen, which is quite electronegative. So that makes sense that they'd be, up here in this neighborhood around 40 parts per million. Therefore, this is going to be the correct answer. D. Let's try a problem that deals with mass spec. Question 19 says, which compound would show major fragment ions at a mass overcharge of 73 and 59? I'm going to give you a second to take a look at this one. All right. Well, if you have some scratch paper, the first thing you'll notice is that all of these compounds have the same molecular formula. All are C5H12O. That means that they all have a mass of 88. That's going to be the molecular ion. So if I have ions at 73 and 59, if I take 88 minus 73, that gives me 15. That means I'm going to have lost a methyl. If I take 88 and I subtract 59, that equals 29. And that's going to come from the loss of an ethyl. Well, if I look at A, where I would get a resonance stabilized fragment would be due to the alpha cleavage next to the alcohol, wouldn't it? But that would mean I'd lose an ethyl and an ethyl, which is consistent with this, but I wouldn't have loss of a methyl. If I look at the alpha cleavages that could occur here, I have loss of a methyl, but here I would have loss of a propyl to get a stabilized ion. Here I'd have loss of an isopropyl and a methyl. Still doesn't make sense. But if I look at D, the fragments at minus 15 could come from loss of a methyl, loss of this methyl, or loss of an ethyl. And so the answer must be D. Question number 20. Which structure for a molecule with the molecular formula C11H14O2 is in best agreement with this carbon-13? We've got a CH3, a CH2, 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 a CH, another CH, another CH. Here we have a singlet that comes from a quaternary carbon. And then we have another one over here. Well, all of these signals fall in the aromatic region, which is from 100 to 150. So these are all going to be from the aromatic region. They could come from an alkene, but I have no alkenes as a possible answer. So these are the aromatic carbons, aromatic. Let's see if we can figure out whether the ring is going to be di-substituted or mono-substituted, because I have two answers that are di-substituted, and I have two answers that are mono-substituted. Well, if I've got a total of 1, 2, 3, 4, 5, 6 carbons in my aromatic ring, if only one of them is a carbon with no hydrogens attached, that would mean that it's mono-substituted. Now, something that you might be saying, like, what the heck are you talking about? I only see a total of 1, 2, 3, 4 signals. How do you get 6 carbons from the aromatic ring? These two signals are taller than all the rest. So those are probably a result of 2 carbon hydrogens that would be equivalent, like this. 1 carbon hydrogen, 2 carbon hydrogens, that would give you double. Then I have a CH, and then I have a carbon that has no hydrogens attached. The same thing would apply to this one. I have a carbon with nothing attached, no hydrogens, a CH that's equivalent, 2 CHs that are equivalent, and then a CH that is all by itself. So that means the answer has to be either A or B. So they're both esters. The carbon that's the most deshielded must be coming from the carbonyl. Which falls in the range of 150 to 200. So far, so good. Well, the last thing I noticed is that if we have an ester in our molecule, we're going to have to look at the range between 50 and 100, where we have carbon-oxygen bonds. And our carbon-oxygen bond is going to be to a methylene. We see that right here. We have a carbon-oxygen bond here, but it's to a methyl. And so our answer must be B. The rest is all consistent. I have 2 more methylenes, and I have a methyl. Looks good. Number 21 is another mass spec problem. Which compound would show fragment ions in its mass spectrum at 85 and 57? Well, again, these all have the same molecular formula. All are C7H14O. And so they all have a molecular ion at 114. Okay, well, if I take 114 and I lose 85, what do I have? 29. That's going to come from the loss of an ethyl. If I take 114 and I lose 57, that's going to come from, or I see a I see an ion at 57. That's going to come from the loss of 57, which would be a butyl. Now again, since all of these are carbonyl compounds, I'm going to get alpha cleavage at the carbonyls. Which one of these is most consistent with loss of an ethyl, just ethyl, and butyl? If I look at A, I have an ethyl, and I have a butyl. In B, I have 2 propyls. In C, I have a pentyl and a methyl. And here I have a propyl and an isopropyl. And so the best answer is A, the loss of an ethyl and the loss of a butyl to give a stabilized ion. Last question, question 22. It says an unknown compound was found to be unreactive towards chromic acid and gave this infrared spectrum, which is a likely structure for the unknown. Well, hopefully you can see that right away this must be an alcohol because we have an OH stretch here. All three, B, C, and D, are alcohols. A is an ether, and so we can cross it off the list. Well, what else do we know? If it's unreactive towards chromic acid, what does chromic acid do to an alcohol? When I take an alcohol, like a secondary alcohol, and I treat it with chromic acid, which I make in situ, I'm going to oxidize that to a ketone. I can also oxidize a primary alcohol. Right? I'll oxidize a primary alcohol first to an aldehyde, and usually it will subsequently be oxidized to a carboxylic acid. But can I oxidize a tertiary alcohol? If I treat a tertiary alcohol with chromic acid, I get no reaction. And so the answer must be D, because it is a tertiary alcohol.